Hello, and welcome to our webinar, Mastering Post-Test Data Processing. This is part 3 of a 3-part webinar, so we will be done after today. These webinars are recorded and cameras and microphones are disabled by default, but these recordings will all be made available at www.mpihome.com, which is M plus P International's website. And they will be on-demand webinars. So basically anyone who wants to see them after the fact can download the videos from there or stream it. So let's get started. Today we're going to take a look at post-processing. This is going to help you ensure that your acoustic field is uniform, diffuse, and you're going to take a look at the amplitude of your responses from the test article. So we're going to show a couple examples as to how you would do that. And your presenters today are Eric Friedlander, who is CTO and co-founder of Acoustic Research Systems. He's a bachelor's of audio technology from American University in Washington, D.C., and he was the product manager at Harman Professional for the JBL Professional Tour sound portfolio before co-founding ARS. So he's got lots of DFAN experience, and now, because of the testing environment that he works in, he's got lots of experience in actual data processing as well. So Eric, you want to say hi?
Awesome. Yeah, no, Dale, thanks for the introduction. And anything I know about data processing, I learned from you. So that'll be a reflection on your training. But yeah, no, I'm
Thanks.
I'm really excited to be doing this with you. For those of you who were with our first series, Dale's the North American application manager for M plus P. He has studied computer science, acoustic, mechanical, many types of engineering, and Northern Virginia Community College, Oakland, and Berkeley. Extensive experience in environmental testing and over 14 years of test engineering experience. For those of you who don't know, Dale and I met in an environmental test lab where he was running testing and I was doing acoustic testing. So we go way back in this field, and very excited to be here. So let's kick into the agenda. So today we're going to talk about data acquisition topics. So this is now we talked about the pre-test, and then yesterday we talked about the test, and now we're going to talk about what happens after a lot of what happens after the test. So talk about time processing. We're going to octave and spectral processing of microphone data. We're going to talk about coherence, diffusivity, and uniformity, sort of garnering some of those features from the acoustic field. We're going to talk about operating deflection shapes from acoustic excitation, looking at hardware, low-level pre and post analysis, which is a really important part of the acoustic test, and then comparing heritage data. So with that said, Dale, you want to start on the first section?
Yes, sir. So yesterday we left off at data packaging, right? So this is what you would want to deliver to the analysis group or customer. And one of the primary components was time domain data. So in this section, we're going to examine some of the key parameters of post-processing time domain data. And a small detour just to set the stage here. There's a few ways to process time domain data. The first is using proprietary scripts in MATLAB or simulation software, or even manually in an Excel spreadsheet. The second is to use a general processing software like the M plus P analyzer that we're going to show today. And the advantage of using the analyzer is that you can capture data while processing FFT in real time, as well as post-processing data. And additionally, user scripts can be combined with built-in reporting tools to help speed up the workflow for field laboratory and noise and vibration products. So I always recommend to trust but verify data from any of these software methods. So some of our customers utilize both methods periodically just as a sanity check. And in addition to this, we're also going to be talking a little bit about simulation software for predicting, using analysis to help predict some of the results that you're going to see. And software like Dassault Systems Wave 6 is another good way to do that for acoustic fields. So detour over. Let's take a look at why we would post-process data in the first place. So post-processing time domain data can save time because it's done in parallel to the actual testing procedure. Personnel requirements may dictate in your lab that the processing is done by another person or group. And if heritage data is to be compared, it's useful to have the time domain data to reprocess whenever newer software or techniques are available, because the time domain data is where it all starts. And as mentioned before, it's good to have that data to verify that the FFT and engineering units are being correctly converted in the software or in the scripts that you're using. And data obtained with incorrect sensitivities, if you have the time domain, can even be corrected by applying a gain factor. So what you see off to the right here is a time domain plot. This one's actually from rotating equipment, but it's just an example here. But essentially, the time domain data has seconds as the x-axis almost always. Could be milliseconds, could be nanoseconds, but seconds is usually the way it's defined. It has equidistant properties. So from one sample to the next, it's always the same distance, and that can help define the sample rate. And it usually has a peak value, right? So this one's in peak voltage, but you're typically recording in peak Pascal if you have microphones, or G if you have accelerometers. So when processing continuously recorded time domain data, it becomes necessary to break that entire recording into blocks of data, and that's what we call a block. Each block may not begin or end at 0 amplitude, such as the one that you see off to the right here. So it's often necessary to kind of pinch off the ends of each block, and we can do that with a process called windowing. So when you look at these different types of windows, you can basically see how they would attenuate the signals at the beginning and end so that it starts and stops at 0 while still maintaining the frequency components of this block, or of this particular block of data. And when would you do this? You'd want to do this whenever you're integrating acceleration for velocity or displacement, because any little non-zero measurement at the beginning or end can be processed as leakage and can show up as a low frequency element. So if you've ever seen data that just has a low frequency shelf and then it starts to increase in the frequency domain, it's very likely that you have a DC offset or you have some sort of leakage going on there. And you'd also want to do this anytime you're doing FFT processing. So if you're moving from the time domain to the spectral domain, this is what you would do. In the example shown here, you can see that for the periodic events, windowing can be really effective at producing a measurement that starts and stops at 0. However, if there are any transient events at the end of the pulse, for instance, I just basically put a marker here, but if this were a transient event and you were to window that transient event, it would show up almost as a non-event in the windowed menu. And this is where processing with overlap can actually help capture some of the obfuscated data, because information at the end of one block could be positioned in the middle of the next block by using, say, a 50% overlap when you're processing data. So now, just a brief overview of time domain data. We're going to scoot over to octave and spectral processing, because these are the most common types of processing used in acoustic testing. The first process is fast Fourier transformation, or FFT, and that's used for nearly all frequency domain techniques. Rather than slap a bunch of equations on the screen, I liked how this animation kind of showed the process of how it achieves the amplitude at each frequency of a time domain signal. And so basically what happens is when combined with a series of filters, the FFT can produce accurate results. And when used with filters, leakage or smearing of the data can occur, obscuring the results, which we'll talk a little bit about later. So power spectral density, acceleration spectral density, which are generally interchangeable, but typically we use PSD in the aerospace industry, are essentially the same thing, right? And they provide spectral data in G squared per hertz from an accelerometer or Pascal squared per hertz from a microphone. They also typically come with a GRMS value, which is the RMS value of the entire block here. Frequency response functions are processed when a force input and an acceleration response is compared, and those are not to be confused with general FFTs, but they do use FFT in the processing. So in random noise testing, the PSD or ASD plots are then processed, and either a linear or exponential average is shown. And these values are expressed as an absolute values in either peak or peak to peak in G squared per hertz. A probability density function can also be applied that helps explain the kurtosis, or how peaky that data is. So higher sigma peaks are more stressful on the part and the shaker, And some amplifiers, like audio amplifiers that we use for the ARS Neutron, they actually require sigma clipping in order to avoid amplifier shutdown or damage to the transducer. This is also common for shakers, which used tube amplifiers in the past. But how this data is averaged determines its usefulness in post-processing. So here we show a time history block on the left, and you can see it looks, relatively peaky. This is a random noise signal. And in the middle is the FFT processed power spectral density block, which looks rather noisy. And that's because it's a bunch of single averages being shown in succession. On the right is the PSD with a linear average of many blocks. And this is why it tends to smooth out and reveal more of the modal properties of the device under test. Now, the reason I'm going over this is because there are two ways to display that data. This is the first one is the linear averaging, which we're showing here. Second is what a random vibration controller uses, and that's exponential averaging. So typically when you end a vibration test, you see the exponential average at the end of the test. And what that means is the most recent measurements matter exponentially more than measurements from long ago. So if it's a 60-second test and you first started that 60-second test with an over test, and then you start averaging, at the end of that test, you might show that everything's perfectly within specification, but you may not know what happened earlier in the test. So it's really important when you're doing acoustic or when you're processing acoustic data, both acceleration and octave data and narrowband data in the spectral domain, that you use linear averaging to properly characterize all of that data from the full exposure of the test. So if you're running for 60 seconds, for instance, every second of that 60 seconds is averaged linearly together. So you get a true mean of the data. Similar to rolling averages, for octave data, that PSD data can also be lumped into rolling average groups from single block data or shorter averages. And what that means is that we can help identify standing waves that are not persistent because they're environmental or electrical in nature. So you can actually use this as a troubleshooting tool to identify maybe an amplifier that's failing, or a room mode or something else that's going on in your acoustic field. And this process is really similar to the octave data that we showed in the previous portion of the webinars, in that there are multiple blocks or short duration averages, and those are all grouped together on a waterfall plot. So it kind of has that look from like, Winamp, down when we used to download MP3s, and you get this cool looking visual screensaver. And you can actually watch these come in real time if you're taking data in M+P Analyzer. So you can see frequency shifts as they occur. And you can use cursors to help show, which portions are linear and which are not. And low frequencies in this case are less accurate in this type of testing, for some reasons that we're going to explore. But basically, the octave data tends to show more accurate results in low frequencies, and PSD data does a little better for higher frequencies, or at least as good as octave measurements. So the aforementioned FFT algorithm also assumes that the process signals are periodic in nature. And since the measured signal is broadband in nature and not periodic, using spectral processing can often lead to an effect known as leakage whenever windowing functions are used. So we have to use windowing functions in order to process the data for spectral domain, but we're kind of stuck with this leakage byproduct. So this is why we tend to gravitate toward proper octave processing. So here we have an example of such leakage from a 50 megahertz signal with various windowing functions. And you can see the different types of smearing and leakage that kind of occur here. It seems that when spreading out a lot of these signals, the spectral leakage would not cause an issue. So one might be tempted to qualify or control an acoustic field with using PSD, where the target spectrum is converted from third octave requirements. So let's do that in a little example here. This was done by our own Raf Mangelschatz here at M+P International. And what you see here is that the PSD appears in spec, right? When you look at the reference. So everything here kind of looks within the lines, and I would have looked at this and said, yeah, it's beautiful. This is perfect. But what happens is that this is smoothed over a long duration, right? It could be like 10 or 30 seconds of averages because of the way that power spectral density is averaged in a random vibration controller. However, in octaves, we can see here that right here at about 63 hertz and in some areas under testing, we have a 5 dB overtest here, right? So if we were to plot this, I didn't have one with the abort lines, but from here to here is about 5 dB based on the scale. You can actually see that the lower frequency octave issues can be revealed in third octave, which is why we tend to control via third octave. It's a much faster response in that way. And how that works is we use ANSI 1.11 as a guide to avoid the smoothing and leakage effects of FFT processing. So by applying a series of carefully specified bandpass filters, along with sophisticated hardware anti-aliasing, we can provide pretty fast and accurate results, especially where low frequencies are concerned. And low frequency accuracy is of critical importance due to the consequences of applying acoustic energy to large flexural absorbers like solar arrays, reflectors, and structural components. And those components are typically inherent of spacecraft. So here we have our first example of octave processing. What we're going to do is we are importing the recording. We can then move our cursors on a time domain scale in order to select the beginning and end of this test. So here we've got a 60-second portion selected. If I can get the cursor there it is, 60 seconds. So then we select the acoustic mode, which activates the acoustic tab, and that allows us to move on to the next step, which is to select the parameters for the acoustic setting. And the way this works is once we have a recording imported into M+P Analyzer, all we have to do is right-click on that recording and say Process Setup, and it automates adding this little post-processing file link right here for you. So it's a really easy way to drag and drop a recording and then start processing immediately. So in the next step, we are going to the acoustic tab, and we're going to select from 20 to 10 kilohertz because this is what our test specification defines. We choose a linear average, and we choose that to go every 4 seconds because what we're producing is a rolling average that we're going to see on the screen when we actually start recording the data. We recorded the data at 32,768 so that we have a 12,800 hertz bandwidth. And then our block size is the same, which gives us a 1-second block. Now along for the ride, we can record PSD. So we've just selected PSD with a linear average of 60 seconds and put a Hanning window on it, just as we discussed before. Finally, we move over to the Save tab, and we can choose to save time history recording or not. And we can choose to save PSD and octave. And that's what we're going to do. So really, we're just laying out the PSD and octaves. So here's the live processing example. So on the left, we have the PSD window, and you can see these PSD blocks coming in, which is why they look rather noisy. We have averaged PSD. We have averaged octave. And then here's your rolling averages coming into the cool, waterfall plot here. So notice as we process this that the block PSD shows much more variation than that average. This is where we're saying this is truly a linear average, right? If there were a whistle in here that popped up sometime in the middle, it would get averaged into this particular measurement. So now we have this data in our workspace and we can take a look at it, right? So if we go into it, in the next section, we're actually going to dive into processing coherence, diffusivity, and uniformity so that you can start to take a look at what these kinds of process data means. And if you look at this, I wanted to show how these two things are kind of confusing. And I jokingly put, A minus B equals X, because it doesn't always make sense when we look at this. These are from two tests that are actually not the same, right? And they look very, very similar. So one could throw these PSDs on a plot and say, you know what? This is a great field. Look at that. It looks very diffuse. It looks very uniform. It looks incoherent. But what we can reveal between these two in the next section is about how constructive and destructive interference and processing a single location or averaged locations is never sufficient in revealing the properties of the test. We really have to look at coherence between all the control microphones and the measurement field in order to determine whether it's diffuse and uniform. So for that, I'm going to hand it over to Eric Friedlander, who's going to take the reins for this section.
Awesome. Thanks, Dale. Yeah, no, great point. I mean, it's one thing to look at frequency response, and as we saw the other day, even if you're running, a single output, a CISO situation, and you look at the control mics, they might look all right. Frequency response doesn't necessarily tell the whole story. So, next slide, please. So, first thing that happens here is we're going to talk about actually processing, post-processing for coherence. So you can see we've got to set all of the microphones to excitation sources, effectively saying that each mic is the source so that we can compare them all to each other and look at how related they are. And then you can kind of step through the steps there where you solve for principal input spectra, and then you go through to the end and you just want to select that you're saving principal input spectra, and that'll end up spitting out both your principal input spectra and also your coherence data between microphones, so you can start to compare microphones in the field. Next slide, please. So what you end up getting then, the results are, what you see on the left is the principal input spectra, which is a way to compare microphones and sources to each other. But what we're really looking for here is on the right, as you can see it building that linear average, is the average coherence and the average relationship between all the microphones. After it's processed, it's really easy to take that data and average it down. So you could do an entire run and you could look at all the relationship, the incoherence of the microphones to each other. You could then average that out, save it, and run another test. Look at those individually, look at the average, compare averages from test to test. So there's several different ways to look at it to give you good confidence that the field is uncorrelated, comprised of uncorrelated sources, and giving you that low coherence that you're looking for. It's also important too, just a reminder from my notes here. If you sort of over average and over space mics apart, it's possible to make things look less coherent than they are. And if you under average, or if you put a whole bunch of mics right on top of each other, they might show a high coherence because they're seeing similar parts of the field to each other. So there's only one way of looking at it, but it's important to keep some of those practical considerations in mind. Next slide, please. So, and then here you can just see the process for comparing the averages to each other. So using a calculator function and analyzer, which is really cool. Admittedly, I only know two of the features in it. One of them is averaging, but it's really easy to grab a couple traces and average them together across the entire stack, and you end up with that single average trace. So now you have the individual traces, which you want to look at, see what's happening, and then you have the average to look at as well easily, which tells you the trend of the data and lets you compare trends across runs. Next slide, please. Why this is important is because you want to look at the individual mic data, but get very busy. You want to look at the average, and it tells you the trends. And so this data set from a paper we presented last year, where we stacked a vertical column of neutron devices, and it was about 5 devices, and we vertically ran 5 separate uncorrelated drives in one test. And then we ran a single, basically fully correlated drive to all of the neutrons in a second test. And you can see the average coherence for both of those, the sort of incoherent or uncorrelated column in blue on the bottom, and then the fully correlated sort of line array, line source column in red on the top there. And, looking at that average at a high level, we're looking for low coherence, right? We're looking for a low relationship between acoustic sources, and therefore a low relationship between microphones in the field. And so looking at this average, we went, okay, if we're running vertically correlated like a line array, that's really, really strongly coherent, and we're seeing some spikes in that. We wanted to dig further in the data to see what does that tell us, right? So this is kind of a way that you can potentially troubleshoot even from a set of averages where you might see spikes in coherence telling you there's a stronger relationship between sources. That. So next slide, please. So then what we were able to do was effectively take a transfer function of some of the microphone, one of the microphones in the vertical column into another microphone in the vertical column and start to look for similarities in frequency response in the PSDs. And in the top, the vertically correlated, the sort of line array column showed kind of what we expected, was that where there's this extremely high coherence, this high relationship, you effectively have a interference artifact or potentially standing wave coming off the vertical front of this array, as seen in the really strong amplitude spike there between the two microphones. And then to A/B that, we then ran the column with uncorrelated sources, sort of made everything less coherent, and we were able to remove that standing wave by running vertically uncoupled. And then if we go to the next slide, we were able to show that there was a pretty strong relationship between where we were seeing the coherence deviation there, the anomaly in coherence in the fully coherent stack, and the standing wave that we captured between the two microphones. So this isn't something we want to do for every acoustic test. I mean, as we sort of showed, if you use the neutron sources with uncorrelated sources, you eliminate these problems. But when we were demonstrating the benefits of this approach against some of the existing legacy approaches, this was the level of detail we went into. But where this is important in a practical sense is, next slide, please. If you look at, let me back up a step. The reason that we're comparing microphones to each other in the field is to effectively confirm that the sources, the acoustic sources that those microphones are hearing, or whatever the field is in that area, is of a low relationship to all the microphones around it. So it's one way to verify the field, is low coherence all the way around. And if you look at NASA Handbook 7010, using an older approach, they say put a ring of microphones, and that ring tells you, and it's easy to look down from your top-down view and see, yeah, these microphones are spaced apart, and these sources are probably unrelated from each other. So we're getting indications of a uniform diffuse field where the sound is highly randomized and even. And you can see that on the left side, where we had 32 drives for a neutron system. And if you're looking in that top-down view going across mic pairs, yeah, they're all low relationship to each other using uncorrelated sources. Dale, is there an animation? You want to click once more? Yes, there is. So what the key takeaway here is on the right side is looking vertically up the microphone pairs as well. So comparing one of the mics on the ground to a next one up, one of the mics on the ground to another one up. When you're using a system that is uncorrelated, using uncorrelated sources, and is incoherent both horizontally and vertically, which is much more similar to reverberant chamber, which is much more similar to the characteristics you want from a real acoustic test, not using a concert system, is that the horizontal and vertical incoherence is very similar, right? You have a low relationship between sources, which means you're reducing interactions and standing waves in the field. And you're able to do that in all three dimensions, which is what your flight hardware wants to see. Where this is important is on the bottom, when we ran horizontally decorrelated, but vertically correlated like a concert line array, then you have this extremely high coherence vertically between sources that doesn't really match the horizontal coherence. And this is one of the places too, where if you just average that all out, it might look okay when they're all averaged together, but when you look at the individual data points, that's where it's really critically important to see how the system's behaving. And then another way to look at the field that I'll just throw up here, one more slide, please, is you can compare the results of the microphones, the coherence of microphones, to an ideal diffuse acoustic field. In an ideal diffuse acoustic field, high level is a sort of theoretical space where the sound is infinitely bouncing around and randomizing. And so it's infinitely uniform, and the relationship between source and transducer picking up the sound. There's an extremely low relationship, and because it's so randomized, bouncing around all the walls in a chamber, for example. So in these images, the blue line represents your sync function for ideal diffuse acoustic field. The black line is the average of all the microphones in the previous study I showed you. And so this is a way to sort of remove dimensions from the microphones and remove the space and really just look at how unrelated are they from each other. And in this case, the neutron system with the uncorrelated sources gives a really good correlation to a ideal diffuse acoustic field, which is, a sort of a theoretical space, but still a good goal to aim for. And it's doing so both horizontally and vertically. So that means you're getting a good incoherent, uniform field all the way around. So two different ways to look at it. Comparing mic to mic is really good for looking at the diffusion system, the DFAN system, sorry, and comparing to an ideal diffuse field gives you some good quality control and some consistency from program to program. So with all that being said, Dale, I'm going to hand this back to you to sort of talk about the next topic, and I'll dive into the chat here while you're doing that.
Thanks. Yeah, I'm glad you set up the idea about the diffusivity here, because if we go back and look at this portion here, this is what we're comparing in the next section to a mechanical response of a system. So we're actually going to look at a solar array response. We're going to use impact modal in order to figure out what that response should be. And then we're going to take a look at when the system is operated this way, which is, we would argue, ideal. And then when it's operated this way, which might be chosen to make more power. So scoot over here. So here we've applied that geometry of a spacecraft with the acoustic energy from the previous coherence example. And here we've got the linear average of the PSD data from each accelerometer. And this just kind of gives us an idea of what the average response is. So each measurement corresponds with a node in the geometry shown here. So if we look at this particular one, this is 148 hertz, for instance. And that isolates the motion of the structure for this particular input. So when you're in M+P Analyzer, there's actually a slider that you can move on the frequency domain that will provide you with these animations, which uses the phase information from the PSD, as long as you have a linear average, to provide these deflection shapes. So note that the type of input and boundary conditions, or the way that spacecraft is mounted or test article of that structure, will definitely affect how these modes look. So if you hung this thing from a crane, the mode might look different or be at a different frequency because certain portions of that are mounted to fixtures which are more stiff. And I should note that using operating deflection shapes with acoustic excitation certainly cannot replace a properly executed multi-degree of freedom modal test, because that will help you correlate your finite element models in a more controlled way. This basically just gives you an idea of how your test article is being excited from the acoustic field, and then validates that the excitation method is adequate at energizing the mode shapes of that particular structure. So we know from that previous impact modal test that the 148 hertz mode, this is a coupled mode between the two solar arrays. So if we look at the animation again, you can see the two solar arrays here. I swear this is not a TIE fighter from Star Wars. This is a real test article, and it's actually a big cylindrical structure, but this is just where we put the accelerometers. So you get this little Easter egg there. But we do know that those two are solar arrays, these two big panels, and we know that they have this coupled mode that's excited by any general excitation at that particular frequency, right? So since the large solar arrays act as flexural absorbers, kind of like a piece of drywall, in the low frequencies, they're especially susceptible to both hot and cold spots where that coherence or more coherence is present. So in this case, the field which is more coherent is providing destructive interference precisely at the location, causing the model or the mode itself to be muted. So if you think of it like this, where each stack, and this is an actual drawing of the test setup that we used with the ARS neutrons, we summed all of the sources for the stack 1, then put a different source to stack 2, then a different source to stack 3, and so on. And what that did was to emulate a typical line array system, because the concert line array speakers require coherence from each other in order to produce the power. Now, because the neutron does benefit from that kind of power, but isn't as susceptible to the kind of lobing that you see when you use a line array, we were able to take that source and put one source to each individual neutron. So we used a total of 32 sources. And when we use 32 sources, that's getting closer to the maximally incoherent field, which we believe is producing a more diffuse result. And what we found is that in this general region right here, you can see the mode being excited by the incoherent field, and you can see the mode basically being notched right out, almost as if there's some kind of destructive interference for that particular mode. Now, when we compare the two modes from one test to the other, you can see the muted mode only affects the solar arrays, right? So that means that the low frequency nodal spot or cold spot or destructive interference in the acoustic field is only affecting those two frequencies or these two parts. Whereas you can see about the same deflection from the structural surface, which is a big cylinder, you can see that happening in both of them. So it's getting excited. It might even be generally excited by the entire broadband random nature of the acoustic field. But the solar arrays are the only ones affected. And the reason we talk about this so much is because you cannot occupy the space of the test article with measurement microphones. This just isn't possible. So if you tried to do that, you wouldn't have any kind of response there. So by taking a linear average of the PSD, as mentioned before, this provides the phase information, which is critical to processing an ODS. So here we have an example of that, where we're taking we're going into the operating deflection shapes. We're taking the power spectral densities, which have that peak or have that phase information as well as the peak amplitude, and then we can move the peaks and select which ones we would like to isolate for the model. So here you can see another mode, which is where the solar arrays tops are excited, but the bottoms are fixed, right? And this is probably due to the way that the solar arrays are mounted to the structure. And then we can go to our what is this, 65 hertz mode, right? So there's another solar array mode where they're both interacting in this way. That's similar to the 148 hertz mode. And what we're doing is we're just saving all of these, right? So as we move through the peaks, we save the shapes, and then we end up with all of these as mode shapes in the M+P analyzer software. Once we have all those mode shapes in the software, we can simply export all of them to UNV or UFF, and that could be applied to a finite element model system so that you could possibly correlate some kind of predicted responses. We actually wrote a paper a while back where Wave6 did just this with a known panel of a known size. They made the predictions. They gave us a plot of what they thought the response in PSD would be. We ran a test and then we compared the two, and the results were shockingly similar. So you can use simulation to provide good results in that case. So now we're going to take a quick look at another feature of recording all this acceleration data that we saw on our modal test. But the standard PSD can also be used without being heavily processed in any way, just for a more routine operation. And this operation is known as a workmanship test. A workmanship test can help you determine whether or not your structure is assembled properly, right? There's lots of bolted joints, there's bonded joints on your structure. If you have a large satellite that you're testing, there are a whole lot of ways that this system could fail, right? And all of your quality assurance processes and mechanical engineers do a great job of getting those things together as well as possible. But sometimes things slip through the cracks. So when you do a workmanship test, you do a low-level test in the beginning, followed by the full level test, which is stressful, right? And if something were to go wrong, we expect that to happen during a full level test for either acoustic or vibration. Then you do a low level post. And by comparing the two low levels, the pre and the post, you can see if there are any major frequency shifts. So here's an example of how that data may be used in the pre-post overlays. For this one, we have a specific tool designed to compare the peaks of a certain quality or Q factor for frequency and amplitude shifts between the post test. And any frequency or amplitude shifts are identified by a pass-fail criteria here. So as we scroll through these processed results, you'll get a nice green light for however many peaks you decide to choose and at what peak epsilon or how or the quality factor of that peak. And then it'll give you a red light if those are not, if that doesn't meet the pass fail criteria. So in this way, you can quickly thumb through, hundreds and hundreds of channels of data and do some pre-test analysis or rather post-test analysis to determine whether or not to continue to the next level if you're doing a vibration test or whether or not the test is valid when you're doing an acoustic test. And I talk about workmanship a little bit here because for some testing campaigns, especially if you're a startup and you're making a new type of spacecraft, or maybe you're a college or university and funding is scarce, there have been situations where the launch vehicle manufacturer was able to waive vibration testing in lieu of acoustic testing. So as long as acoustic test was met without any compromises based on their specification, you can do some work and analysis work to try to call that acceptable for launch. Now, I think the exception there is for sign burst testing, where if you have a lateral launch payload on your spacecraft, you have to simulate that some way on a shaker table. But if that's not required, if sign burst is not required because you're launching normal to the mounting location, you might be able to get by just doing an acoustic test. And the way this system is designed is that we could actually configure it with just say three devices for a small like 12U CubeSat, for instance. So it's actually possible to do these tests pretty low cost. So another way to process this data for pre-post is a bit more automatic, and that is through a reporting tool. So by choosing a report that includes all the workspaces in the file and grouping by name, the report can simply be made in seconds, which shows all of the overlays. So here it is thinking about all, hundreds of pages it's going to display. And once it loads that, as you thumb through the report, you can see that each overlay is defined in a PDF. And it's not, when you make this kind of PDF, it's not that you're stuck looking at a piece of paper. You can actually choose peak amplitudes, numerical values, Q factors, and damping for multiple peaks, and those can be processed for each measurement and can appear on either the plot or somewhere in the metadata. So this can help an analysis team or customer make informed decisions just from a piece of paper. And sometimes those reports can get quickly filed into the test articles process paperwork, and that can give you a good overview of whether or not your test was successful or not. So that was basically pre-post testing. So for fleet systems or structures with iterative designs, it may be useful to compare data not just from pre-post, but from one serial number to another. And we've done some work with fleet satellite manufacturers where they're making hundreds or thousands of these things, and it's good to kind of have a baseline specification from your qualification unit, but then start to look at each individual component for trending. And that helps you keep an eye on component degradation or maybe an issue in your production process and even facility maintenance. Every time you run an acoustic system and you do an initial shaping run, or you do a verification system every year by running a test just on its own or with a dummy mass, you should be comparing the voltage draw, current, the impedance of the speakers, which I know the ARS drive does a good job of monitoring, and then look at the drive output from your control system to make sure that 1 volt equals 100 dB or whatever that scale might be. So what we're going to do here is I'm going to close the presentation and we're going to move over to M+P Analyzer for the duration of this. So I'll end the slideshow. Here's our little hummingbird, and here is Analyzer. So let's make this a little bigger here. Okay. So what we've got here are some data sets, right? We've got a PSD plot here, this is a 2D window. 2D windows can just be added by, clicking on the 2D section. There's also multi-chart, animation, and waterfall windows, and this is a waterfall plot on the right. So what we're doing here is to take a look at PSD data. So I'm looking for 32 drive, Gram A, right? So any one of these can be brought into the 2D window. So I just hold Shift, drag some up. I can hold Control to add one if I want to, or I can hold Shift, let go of it, and then that replaces whatever's in the window. So one way you may want to do this for heritage data, let's say I've got two similar tests that I want to compare, is I can right-click on this 2D plot, go to Properties, and then I'm going to choose the Q, the damping, and the peak high, and this is going to be for the first 4 peaks that are selected. And I'm going to put that in a pop-up window. What that does is it gives me this kind of semi-transparent window here that only looks between these two cursors. So if I remove cursors, it's going to look at the entire data set. But if I do this, where I just isolate it to say this peak, I get one peak here. Let's see if I can move this. Right, so now I've just isolated it to this one peak. So I got to make sure to capture the whole thing. And this just gives me the one. Or I could open this up to more peaks by opening it up to the entire data set. Now this data is really noisy, right? So these Q and damping factors are more isolated to some of the noisier peaks. But if I happen to have a really nice clean measurement, right, from like an FRF, for instance, I can do this, and this is going to capture really beautiful peak values, right? So I can do that for multiples, and if I have quite a lot of these, like this, it just makes the table bigger, essentially. So I can drag these over and take a look at those responses. So now this table, I could actually just copy and paste into Excel, and I keep doing that every year or every part to look at trending. So that's just peak picking. If we were to go back to this value table, you can see there's a whole lot of other things I could do. I could do mean, I can look at the RMS value of certain responses. And RMS is another good way of trying to characterize the response of a test article from one test to another. So if you're testing to 150 dB, for instance, and you put a test article in there, and you get one set of responses when you're doing for the first 150 dB test, you process that same test a year later, and then you do not get the same RMS responses. That's something you have to think about. So the next part I'm going to go over is just using these plots, right? We talked earlier about how those waterfall plots can show you basically elements of a test which are happen sooner in the test rather than later. So the way we do this in M+P Analyzer is simply to take these rolling averages. These are actually imported directly from Vibe Control, so you don't even have to process them, but you could process them similarly to how we showed you earlier when we set up those rolling averages in the data set. Now, if I right-click on the measurement set and I group by name, you can see in the workspace here, there's a whole bunch of them with 4 averages each, right? So this is PSD of channel 1, and I've got all of these have 4 averages because they were 4-second rolling averages. And then the last one is 1 average of the entire data set. So I can just take this entire thing and drag it up here into the plot, and then that gives me that particular location. So you can see as we move from one to the other, how this changes from the response. But it looks pretty even. We're not seeing any major frequency shifts along the line. If I drag my cursor here, which is probably not the best color for the red. If I made it blue, it would be a little better. But I can take that cursor and look for frequency shifts over time. So this could be all from the same test, or it could be from iterative tests over the years. So we're coming up a little bit here on the end. I was going to try to leave the last 10 minutes for questions or so. Does anyone have any questions about the processing of the data? I know it looks like Max asked a question about 1, 6, and 12th octaves. Eric, did you answer that already?
I have not. So Max and I
Okay.
were chatting about the drive, the configuration, which I addressed. But yeah, anything on
Hmm.
how you guys drive, it's your ballpark.
So we haven't seen any specifications come in with 1/6 and 1/12 octave. If we did, we would probably implement that. I should note though that the more filters you add to that filter set for octave processing, the longer it takes to process each section. So, we have not, with modern processing power, I'm sure it's not an issue, but typically because of that low frequency accuracy that we get from applying those larger filters for third octave or even one octave, um, we've found that we can respond more quickly. The more you take, or the higher the fractional division of the octave bands, the closer you get to narrowband, where you're kind of isolating yourself to only being able to control high frequencies really well and characterizing them really well. So we've tried to find a happy medium between 1/3 octave and one octave processing for acoustic. And so far, most of the launch vehicle manufacturers that I know of have just specified it in third octave as a result. One, because that's how they measure it, but two, that's how typically it's defined in the process. But it is a great question. Cool. Um, we'd be happy to take any questions offline. I'd like to take a quick moment to thank you if you've attended this entire series. Eric and I put a lot of work into this, and um, we really love what we do, so we like sharing it. We like answering questions, and we like providing solutions. So if you guys come up with anything, just where to find us offline. Um, we have a couple more uh, webinars coming up at the end of the year, and in-person seminars, one for force limiting vibration testing and another for Halt-Haas chamber monitoring. So if any of those interest you, head over to mpihome.com and you can register for those. But once again, I'd really like to thank you for your attention and hope you enjoy the rest of your week.